Linear relationships can be described as either positive or negative. Below are two scatter plots that display a linear relationship between two numerical variables x and y. The relationship displayed in scatter plot 1 is a positive linear relationship. As the value of x increases, does the value of the y variable tend to increase or decrease? And if you were to describe this relationship using a line, would the line have a positive or negative slope? As we look at scatter plot 1, as we look to the right, as x increases, what happens to your outputs? Your outputs are generally increasing as well. So they are moving together in tandem. So if we were describing this relationship using a line, it would have a positive slope. The relationship displayed in scatter plot 2 is a negative linear relationship. As the value of x increases, does the value of the y variable tend to increase or decrease? And if you were to describe this relationship using a line, would the line have a positive or negative slope? So again, as the value of x increases, what's happening to the value of y, the outputs? The outputs are also decreasing. So they're not moving together in tandem. So as x increases, y decreases. So we would have to use a negative slope to represent this. What does it mean to say that there's a positive linear relationship between two variables? Well, as we talked about before, scatter plot 1 was positive because as x increases, so did your y's. They were moving together in tandem in the same direction, both positive, increasing, increasing. What does it mean to say that there's a negative linear relationship between two variables? That means they're not moving together in tandem. So as x increases, y decreased. So a negative correlation exists. So is the linear relationship in scatter plot 3 positive or negative? Again, this is looking at the relationship between numerical values of x and y. So as x increases, what does y do? Y is typically increasing. So we would say this is a positive relationship. Now taking a look at scatter plot 4, again, is this relationship positive or negative? So you're going to look at your variables and see what's happening. As x increases, what does y, your output, do? They are typically increasing as well. So we'd have to say this is a positive relationship. It's also common to describe the strength of a linear relationship. Instead of just being positive or negative, how strong or weak is the relationship? We would say the linear relationship in scatter plot 3 is weaker than the linear relationship in scatter plot 4. Why do you think the relationship in scatter plot 3 is considered weaker than the relationship in 4? As you look at your two plots, the data values are important. So as we can see in scatter plot 3, we can see that they are typically increasing as you look to the right of your graph. But the increase is a little bit different as what's happening in 4. 4, we can see kind of a line being formed with your data points. It would kind of start here and increase in this direction. So they're kind of more aligned together versus what's happening in 3. We could still say that they are increasing, but they're not in an alignment as they are in 4. So those that are more aligned would have a stronger relationship than those that are not. So we've talked about positive and negative relationships and the strength. Now it's your turn to draw an example. Could you draw what you think a scatter plot that would show the strongest possible positive or negative linear relationship would look like? Please make a scatter plot with 5 points that illustrates each one. So could you give us an example of what you think of the strongest positive linear relationship would look like and the strongest negative linear relationship? We'll have you pause the video and then resume when you're ready to compare graphs. So if I'm talking about a positive linear relationship, as x increases, so does y. If I want it to be very strong, those points need to be very aligned. So I should see that constant rate of change being developed. So this could be an example of what that would look like. 5 data points where we see the constant rate of change lined up. Similarly, we want to see the same idea for our negative relationship. So as x increases, y decreases. So again, those 5 data points should be fairly aligned so we can see that constant rate of change, your slope, being formed. So talking about the strength, this is where the correlation coefficient comes into play. The correlation coefficient is a number between -1 and 1, including those values as well, that measures the strength and direction of a linear relationship. The correlation coefficient is denoted by the letter R. Okay, so if we see R, we have to think correlation coefficient, and it's judged on a scale from -1 to 1 inclusively. Several scatter plots are shown below, and the value of the correlation coefficient for the data is displayed for each plot that is given. What we want to do is determine when the value of the correlation coefficient is positive. So looking at our example here, we see positive correlation coefficients for our first 3 graphs. And why do we think those are positive? Well, as looking at the data values, we can see as x increases, so does typically our y value. So that's why it would be a positive R value, correlation coefficient. When is the value of the correlation coefficient negative? So when is the R value negative? Well, we have 4 examples of those where the R value is negative. And what do they all have in common? Well, as we look at each of those 4 graphs, we can see as x increases, y typically decreases. So they're moving not in tandem with each other, and that is why the R value is negative. Is a linear relationship stronger when the correlation coefficient is closer to 0 or 1 or -1? Well, as we said before in our previous slides, strong correlations are when the points are very tightly aligned. So if we go back to our picture from before, we know what to look for: a strong positive and a strong negative relationship. So as we look at these graphs again, when does that happen? Well, they're very aligned here and here. And those values are 1 and -1. And as we travel away from 1, notice how the alignment shifts, but we can still see the trend of the points fairly well. We don't really see a trend when they get further away from 1 and -1 like they do here. So we know that when the when the correlation coefficient is closer to 1 or -1, it's very strong, and it becomes weaker when it travels away from those values, so as it approaches 0. So what we want to do is take all of these items now and put them into practice so that we can come up with lines of fit for our data and use those to make pretty accurate predictions based on what we've come up with. So we're going to look at a bird population example. So here the table shows the number of woodpecker clusters in a part of the DeSoto National Forest. To do this, we have to draw a scatter plot and determine the line of fit. And once we have drawn the line of fit, we should be able to come up with an equation that models it, and then as a function of the number of years since 1990. So important things that are standing out. We know that it should be a function, 1 input, 1 output, and we can see that in our table. We also know our independent variable x is the number of years since 1990. So 1990 is acting as our zero, our starting point for taking the data. So 1992 would be 2 years after that, so it should be represented by a 2. 1993 is 3 years after that, so we can represent it by a 3. That will help organize our data points nicely in our graph. So what we're going to do is kind of put those hints in our table so we can very easily plot our points on our scatter plot. So we're going to do that now. We're going to take each of these coordinates and plot them on our graph to see what's happening with the data. Are there any trends? So can we say if it's positive, negative, strong, or weak? So if I plot those points, my graph appears like this. And we can see the data seems pretty aligned, not perfectly aligned, so we probably won't have a correlation coefficient of 1 or -1, but it should be close to that value. And so how are we going to come up with the equation of this line? Now, typically we have two ways to write the equations of the lines: point-slope form and slope-intercept form. So we need to create a line and see which of those would be the best option. So when we create our line of fit, we need to make sure it's going in the direction of the data points, and we need to have at least 2 data points on the line, because when we come up with the equation, we have to find the slope, and we need 2 points to do that. We also want to make sure when we're making this line, it's dividing the remaining data points evenly, approximately, above and below the line. So as we take our sample line here, we want to make sure it's going in the direction of the points. Well, we know as the years passed, the population clusters went up. So we need something with a positive slope. And then we can start adjusting the line to meet the second 2 requirements. We want to have it go through at least 2 data points and divide them about evenly. So if I look at what I just put here, I have more points kind of below than above, so I want to adjust it, maybe want to extend it a little bit more. So what you want to do on your graph is you take a straight edge and a pencil, and you're going to make that judgment call. You want to draw it so it's going in the direction of the data points, has at least 2 data points on it, and is dividing the remaining ones about evenly above and below. So I'm going to adjust mine. Let's have you draw yours, and then we'll compare to see how closely our lines of fit are. They're probably not going to be exactly the same, and that's okay, but they should be similar to each other. So as I adjust my line, I'm going to come up with a line like this. I can see it's going through my 2 data values, here and here, and I have approximately the same above and approximately the same below. So I'm interested in the coordinates for the data points that I want to use, and so I'm going to use 324 and 842. Again, you're going to use your 2 data points because we have to find the slope of our line. And again, our data points may be different, and that's why we're going to go with what we have. So we know to find the slope, that's the change in y over the change in x. So y minus y over x minus x, the rise over run. So I'm going to find the slope first, and then I'm going to say, okay, once I have the slope, what would be the best way to write this equation? Well, because I have points and I'll have my slope, point slope would probably be the quickest one to start with. So let's try this. Let's find the slope of our line. So the slope of our line, change in y over change in x. So 42 minus 24 is 18, and 8 minus 3 is 5. So my slope is 18/5. Always check to see if you can simplify it. No greatest common factors exist between 18 and 5 besides 1, so we're going to leave that as is. Now we want to take that and put it into our point slope form. So remember, that's y minus the y coordinate equals our slope times x minus the x coordinate. And I have 2 coordinates to choose from. It doesn't matter which one I use, it's still going to represent the same line. So I'm just substituting the coordinates in to my format to come up with my equation. So here's a sample of what my equation would be in point slope form. Now, some of you may have said, well, maybe I want to write this in slope-intercept form. And so we can kind of use the same idea as we did previously. When we have the slope and a point on the line, we could find the y-intercept by substituting one of our coordinates, x values in for x and y value in for y, and solving for the y-intercept for b. If you chose to do it this way, what you could do is now start following your order of operations. We're going to take 3 times 18/5, which is 54/5, and undo that to solve for b. So I would subtract 54/5, or if you want to get the decimal approximate, that would be 10.8, and subtract that from 24, which is 13.2. So we could write our equation in slope-intercept form as y equals 18/5 x plus 13.2, or if you want to use the decimal equivalent of 18/5 as 3.6, that would be fine as well. Now, because our lines are slightly different, we might want to take our point slope equations and put them in slope intercepts to see how close they are to each other. So if we go back and take a look at that, we can easily go back and take our point slope forms and put them in slope intercept. So what we have to do is get y alone. And the first step would be adding 42 or adding 24 to each side of my equation. And then I would have to distribute and combine my like terms. So I would take 18/5 times x times -8, or 18/5 times x and -3, and see what I have left. Again, if you want to convert to decimals, that's fine as well. And then combine your like terms. And notice this is the same equation as what we had previously. Y equals 3.6x plus 13.2. Now, depending on the points that you used, hopefully ours are fairly similar to each other. That means that we have good lines of fit going in the direction of the data points, at least 2 data points on the line, and divides the remaining data points evenly. So whether we use point slope form or slope intercept, we should have a way of comparing to see how on target we are with our data values. So here's our line of fit. Now the question is, how accurate is it based on our data values, right? What's the strength of our line of fit? Well, there's a couple things that we could do. We could take this equation and substitute our values, 2, 3, 4, 5, 6, 7, and so on, and see if the outputs are close to our actual data values, right? That will tell us the strength of our line. We could also put it into a graphing calculator or a Desmos calculator and see how close it is as well. And we'll go into more detail with that in our next lesson. So I went ahead and for my line of fit, substituted my input values into my function to see what output values resulted. And what happens? Well, let's see. Here is my original. I'm sorry, my original is in red, and in blue is based on my equation. And we can see we're a little bit below on this one, on target, a little bit above, 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 and then we're below, on target, a little bit above, and then a little bit below. So we're close. We're not perfect, so we should have an R value close to 1, but it wouldn't be 1. But this is a way that we could do a quick check to see how close and strong our equation is to the actual data values. So now it's your time to practice. You're going to have some scatter plots given to you where you're going to start off by telling us what type of correlation exists, positive, negative, or none. Then you're going to have a couple of data sets given to you where you're going to create your own scatter plot, draw on your line of fit, and come up with an equation to represent it. Then you'll also do some predictions similar to what we did with our woodpecker problem here. Based on that set of, again, can you talk about the correlation that exists and come up with an equation to do some predictions?